now we have discussed both the direct current voltage source. We discussed conductors, which are basically just lengths of wire, and those are what you call passive components. So now we get into what we call reactive components, which are inductors and capacitors. So first we'll go into inductors. And an inductor has a property called inductance, which is used by the letter L. As here we have this Greek letter mu times N. Mu is the permeability of the core material, which is measured in Webers per amp meter. And then, so for and then we have, so that's mu. How permeable is our core material? For example, is it just an air core, like the secondary on a Tesla coil? Is it an iron or a steel core? And they have different numbers, and they'll be provided to you in some table for when you're building a part, or you can Google it or look it up in a reference book. So we have mu times N squared. N is the number of turns T around the core in a single layer, such as a secondary of a Tesla coil, again, or a solenoid. Solenoid being, well, again, I go to the secondary of a Tesla coil, that tower of a single turn of wire. So N squared, that squared factor means the number of turns is the largest influencing factor on the inductance of an inductor of a coil. So, and I'll multiply that by A, which is the cross-sectional area of the core in meters square. And then we take the product, first we square, and then we take the product of a permeability, the number of turns squared, times the cross-sectional area of the core. As if we were looking at the core like this pen, the cross-sectional area would be how wide is that circle of the pen. The pen's narrow diameter there, and then formula for area of a circle. That's our A. And then we divide that whole product by the length of the windings, which is say if I were to wrap a wire around this pen, how long, if I started winding here and I wrapped a whole bunch of turns here, I would measure how long that is and account for the bare wire. This is all the wire coupled right as close to itself as it can be, like the secondary of a Tesla coil. And that length, that's accounted for in meters. And then L is the inductance in Henries that we get. And that's the number that we want to come up with. In fact, I went ahead and made myself a little drawing of what I just described. There's L, the length of the windings. There is our wire, which is our conductor. And this is going with enameled copper wire, so that the wire isn't touching each turn to turn of the wire is not making a physical contact with itself. Otherwise it would just be a dead short across there. So there is insulation around the entire length of the wire. N is your number of turns. A is cross-sectional area of your iron or ferrite core or air core with mu property of permeability. So that is an inductor. Now, inductors have a store energy in the positive direction and release energy in the negative direction. So inductors basically store current, just like capacitors store voltage. So the voltage across a coil is this V subscript L. equals E, your supply voltage, times, e to the minus x. That is an exponential function, which you can find on your calculator. And then this funny little t, that's almost a pi, that's the Greek letter tau, lowercase, tau, T-A-O, equals L over R, which is the inductance, divided by the resistance of the actual coil, as if you were to put your ohm meter across the two terminals of the coil, or just get the whole entire resistance of your circuit. Let's say there was an additional 10 ohm resistor in your circuit, which is what we start with when learning about inductors. And so your Henries over your ohms, that gives you your tau. And then this minus lowercase t, that's how much time in seconds, which will elapse, either the elapsed time that voltage has been applied to your coil, or some factor of tau. For example, in about 5 tau, your voltage across the inductor, your V sub L, is going to drop exponentially. There's 1 tau, one time factor. Imagine 2, 3, 4, and after 5 tau or 5 time factors, you're not going to have a significant amount of voltage across the inductor. Just like when it releases, it's actually, took me a while to get this, but it is a negative value in that the voltage goes actually back up. So that formula here is voltage across the inductor is equal to the E, which is the voltage across the coil. Let's say it's 9 volts or so, and multiply that by the exponential function of negative however many seconds you're measuring across, say 1 second, divided by t tau, which is your L over R, and that will give you your voltage over across the the inductor, which changes with time. See, we call this reactive component because, unlike a resistor, with a resistor the change is instantaneous. There's either so many volts or across or current through a resistor at one time or not whenever direct current is applied. But even if we put a battery across an inductor, which is not very common, it still will behave this way in either direct or alternating current. It will briefly have a voltage, and that voltage will disappear, and it will simply act as a conductor, because an inductor is a coil of conducting wire. So it's going to just, after this very brief time, act like a short. So there's inductors. Oh, and there's also this formula for current through an inductor. And there's another formula there. It's E, your voltage source, divided by some resistor in your circuit, over R. And there you have current through an inductor, which, as you see, goes up over time when it's in the storage phase, because you see inductors store current, and it releases that current in the discharge phase. And then let's say the models that's usually given is to have some separate added resistor in series with your inductor, and this is the formula for the voltage across that particular resistor. It's almost like the voltage across your inductor, but it's 1 minus e to the minus t over tau, and the voltage of the resistor, as you see, will match with the curve of the current through the inductor. That's a match. So inductors can be treated like resistors, and I didn't make a flashcard for resistors in series and parallel because that's pretty straightforward. There's lots of ways. Resistors in series add, and resistors in parallel, well, you take the reciprocal of each value and basically add them up and then take the reciprocal of that number. But it's going to it basically treat inductors the same way as resistors. As you see, we add L being your coil, the inductance of your coil, we just add inductances, and in parallel we have 1 over L1 plus 1 over L sub 2. Or if there's only 2 of them, then we have the product over the sum. And you'll see product over sum all the time. Product being L1 times L2, sum being L1 plus L2, and that is your parallel inductance, which also works for resistors. If you have resistors in parallel, then the total resistance of those parallel resistors will be smaller than the smallest resistor used. Here's a little bit more about that time constant, if it wasn't clear earlier. Tau, the L over R. So it is a Greek letter, as I mentioned. L is the inductance of your coil in Henries. R is your resistor value in ohms. So any RL circuit means a resistor and an inductor in a circuit can store or release current in about 5 tau. That means the inductor can be fully up to the amount of current flowing through the circuit and down to the, well, basically 0 current flowing in it when it's fully charged with current. A little bit more. And because it changes with time, there's also a differential equation relating to inductors. Yes, electrical engineering does need you to know a little bit of calculus. You can get by with algebra for most of it. In fact, just about everything I've been taught in these classes that I've aced, get straight A's in. I didn't really need calculus, but differential equations are about the easiest form of calculus. You can know that in your unit circle and apply in trigonometry. If you know that, then you should be pretty well set. So here's a differential method for finding the inductor voltage. So that means the change in the current of the inductor over the change of time, that's di L over dt. And if your inductance is multiplied by that, that is the voltage across the inductor at any given t for how much time you're measuring. This is your rise over run, your basic, what's the slope of your curve. And it is easier really to use the exponential function as this card mentions. And if it's going up, and there's some large positive number. If it's going down, there's some large negative number. If it's straight up and down for your curve, then it's an infinite change at that particular time. And if it's straight flat, then there is 0 change over time. Think of it as your timeline going left and right. In fact, here it is exactly these kind of curves that this is talking about. As you see where the curve is steep, it is going up, and at this time, this is the slope. At this time, the slope is getting flatter. The change is slowing down. And eventually, it's going to be perfectly flat after so much time passes. All that means is that the the voltage across here says E voltage is 0. There's no change in your voltage. The value of the voltage is equal to the voltage supplied by your battery or voltage source, but the amount of change in the inductor, this is how fast is it the change happening, and when it's not changing, then it's at a stable state. And just like when we release the current from the capacitor, the voltage across the capacitor will drop quickly. See how steep that is at that time? That means it's going down, it's becoming negative. The amount of current is decreasing, and then it's slowing down, and then it levels out to just about flat. There's no more change because there's no more current in the capacitor to be released. See, that is basically your standard derivative function. Okay, we'll do capacitors. So, the voltage of your capacitor, we'll actually start with charging voltage here. Capacitors are kind of the opposite of inductors. As you might tell from the schematic symbol, instead of just a wire coiled up with no break in it, meaning it's a short circuit to direct current. See, a capacitor there's a plate, there's this empty space where the dielectric is. Dielectric means it opposes a flow of current. Its electrons are not easily moved. A conductor means the electrons are easily moved in exchange with its neighboring molecules. Dielectric is resistant to change in current. It's an insulator. Voltage across the capacitor, this is going to look familiar to inductors, so it's your voltage source times 1 minus e to the minus t over tau, and it's going to go up with time. See, voltage source, exponential function, time constant, our tau, and then here we go. This is what you call the transient phase of charging. An RC, so we have a resistor and a capacitor in a circuit. And there's our 5 tau, there's our slope. Discharging voltage, as we see when we compare the graph, is just E voltage supply times the exponential function of minus t over tau, as opposed to 1 minus when we're charging. We're going to get, we're not subtracting 1 from it. So it happens in about the same amount of time. So, as we see, here's our slope. It's negative, and it's very similar to inductors. That's for voltage. Now for current, we have E over R times e to the negative t over tau. Your current, your amps through your capacitor, is your I sub c that we're solving for. So there's your values. So that when we are charging a capacitor, the current through the capacitor is going to drop as it stores voltage, and then in the negative direction it will discharge. This is another one that the current through the capacitor actually goes back up. Or about capacitors, voltage across the resistor and the capacitor. Again, very similar to the resistor and the inductor resistor or LR circuit. Capacitors. Now capacitors have something, because there's two separate plates and there's a separation between them, an electromagnetic field is present. So this curly E, this is our field strength. So this is V over D, where V is volts and D is a distance between the plates in meters, between the plates indicating a polarization of the dielectric material. One side's negative, one side's positive. Even in alternating current applications, where it's both positive and negative, half of the cycle is positive, the other half of the cycle it is negative. So there is polarity in alternating current, but I learned this before AC. This was just with direct current theory. You see capacitors in direct current applications all the time. So here we have the current through the capacitor as a derivative, or well, here I incorrectly called it it is differential. I was right. Derivatives are a lot more involved and long and drawn out and tedious to go through. Differentials are a lot easier. So this is just the slope of our curve again, according to it. And my experience, I found it's easier to use that E over R becomes exponential function a negative T over tau. But that's what I think. Now, when you have capacitors in parallel and series, it works the opposite of resistors and inductors in parallel and series. So in parallel, capacitors add like resistors in series. So if you have two capacitors and tell you their capacitance in Farads equals, you just add them up. And if they're in series, it works like resistors in parallel. So 1 over CC sub T is total capacitance. 1 over C1 is 1 over C2, capacitor 1, capacitor 2. However many you had, you just add them all up. Or it's easier, if you say you have just 2, then you have, again, the product over the sum. And if you're going to build your own capacitor, which is not done all that frequently, but if you really want to, then see your capacitance equals this funny little E. I don't know if that's epsilon or not. It's from the textbook. That's how it was written. E times A over D, where C is your capacitance in Farads, E is your dielectric constant of the material, which will be given to you in a table of some sort. And then we have the area of a plate, just one of the plates. Almost every single application you see, the area of the one plate will equal the area of the other, length times height. And then you just divide that area by the distance between them. Remember to use meters squared for the area and just meters for your linear distance in your denominator. Dielectrical material, it has no free carriers, so there's not going to be any charge in your dielectric. And the plates of the capacitor are conductors, as I mentioned earlier. So capacitors hold charge. So here we get back into charge, like, remember we went through Ohm's law with current and amperes and all that. So our charge is in columns, and it's denoted by the letter Q. And so here we have C is our capacitance in Farads, Q is our charge in column, and this V is how many volts we have across the capacitor terminals. So we have both C equals Q over V. That means our capacitance equals our charge over our voltage. And algebraically, just like with Ohm's law, we also have our we also have Q equals C times V. If you want to know how many columns, 6.24 times 10 to the 18th electrons. If you want to count individual electrons, then you just take your capacitance and you multiply it by how many volts you have. Likewise, you could also solve for, if you know how many electrons you have, you could convert the electron count into columns and solve for your voltage by taking voltage equals your charge, your Q, your electron count per second, and because you would switch the place of the C and the V there, you can see how that would go. Cool. Alright. And then one more card for this particular clip. Capacitors, your tau, your time constant, just like we had for inductors and charging. And we went through the capacitor charging and discharging. That is R times C. I believe for inductors it was L over R. Here it's just R times C. So R is your resistance in ohms, and C is your capacitance in farads. So for any RC circuit, it can be near fully charged or discharged in about 5 tau. Just remember 5 tau for inductors, for capacitors, for charging, for discharging. 5 tau is your friend. And we'll continue with the rest of this stack in another clip. Thanks for watching.